Hello everyone. In this video we will see about degrees of freedom, links and various joints in robotics. Okay, so first we will see one by one. So first is the degrees of freedom. Okay. So degrees of freedom in a robot refers to the number of independent variables needed to describe the robot's position and orientation. In a typical robot, you need a 6 degree of freedom to fully control the motion of its end effector in relation to its base. Okay, the first 3 degrees of freedom determine the robot's main workspace and are controlled by the robot's body through its motors or actuators. The remaining 3 degrees of freedom often located near the robot's tool center point. Okay, act like a wrist to control the orientation of a gripper or tool after the robot has positioned it correctly. So these 6 degrees of freedom allow the robot to reach any desired position and orientation within its operational area. Next, so degrees of freedom in a robot are divided into two parts, that is the arm and the wrist. Okay, so arm is responsible for positioning the end effector in space and it requires 3 degrees of freedom for this purpose. And the remaining 3 degrees of freedom are in the wrist and its job is to orient the end effector. Okay, so whenever you add an independent joint, whether it allows for linear or angular movement to a robot, you are essentially adding a degrees of freedom to the entire system. It is important to note that adding a degrees of freedom to the system does not always mean you have added one to the end effector itself. The distribution of degrees of freedom between the arm and the wrist ensures that the robot can both position and orient its end effector effectively. Okay, so you could see what is the degrees of freedom for the systems here given. Okay, you could see first you have a rotation. Okay, and this you have a two rotations. So one is a linear movement and one is a rotation. So you have 2 degrees of freedom. Okay, and also here in the next picture you could see you have a robot space and for to reach the end effector, how it reaches the end effector, where you could see the dexterous workspace and the reachable workspace. Okay, accordingly you have to calculate the degrees of freedom. So for this system it is 2 degrees of freedom. Next, some of the examples for the degrees of freedom. So first we'll see what is a spatial manipulator. So it's like a robot's arm that can move and rotate freely in 3D space, and it needs 6 degrees of freedom to do so. Okay. So if a manipulator has fewer than 6 degrees of freedom, it can't move as freely in 3D space and has some constraints. And next about planar manipulator. So it is designed to work in a 2D plane. It can move along the X and Y axis and rotate around the Z axis, making it suitable for tasks that are confined to a flat surface. And third is the redundant manipulators. So these are interesting. They have more degrees of freedom than what's absolutely necessary. This extra flexibility can be a boon because it allows the robot to navigate around obstacles and reach spaces that might be blocked otherwise. Okay, it's like having extra tricks up your sleeve to get the job done more efficiently. And you could see the examples. So if you need to calculate the degrees of freedom, or it is named as mobility of a spatial manipulator and planar manipulator. Okay, so first we'll see about the spatial manipulator. So let us consider a manipulator with n rigid moving links and m joints. So here links are named as n and joints are m. Okay, so here connectivity Ci is represented. That is the connectivity of the ith joint. Okay, where I will be 1 to till m. How much number of joints are there? Based on that, we'll have this I. And number of constraints put by ith the joint will be 6 minus Ca, since the maximum degrees of freedom is 6. So total number of constraints will be summation of I1 is 1 to m 6 minus Ca. So here mobility of the manipulator or degrees of freedom of the manipulator in case of a spatial manipulator, it is calculated as 6n minus summation I equal to 1 to m, that is the total number of constraints you will be calculating here, 6 minus Ca. Okay, so this is known as Gruebler's criterion in case of spatial manipulator. Similarly, you can calculate the mobility of the planar manipulator. So again, we are considering n rigid moving links and m joints. Okay, so here for the planar manipulator, only the constraints where we have the difference is that since maximum degrees of freedom, okay, for a planar is 3, we'll be having here number of constraints put by ith joint is 3 minus Ca, and total number of constraints will be summation I equal to 1 to m 3 minus Ca. And for the Gruebler's criteria for calculating the mobility of the manipulator is 3n minus summation 1 is 1 to m 3 minus Ci. Okay, so this is how the mobility of the manipulator in case of planar manipulator and spatial manipulator is calculated. Okay, so next, so we'll see what are joints and links. So think of a robot's joint as the parts that let it move, just like your body's joints. Each joint gives the robot a specific way it can move, which we call as a degrees of freedom. Okay. Now the links are like the solid parts of the robot's arm, and each joint connects two links, one closer to the robot's base. When one link moves because of a joint's action, it makes the other link move in different ways. So the joints are like the robot joints, where the links are the rigid pieces that the joints connect to and help move. Okay. Next, many robots are firmly placed on the ground, and the part that connects them to the floor is called link 0. That is, the base is 0. So link 0 connects to the first joint, which is joint 1. This joint moves the link 1, which then connects to the joint 2. Okay, the process continues with each joint and link connecting to the next one in a series. So this is how the robot's arm is built, one link and joint at a time. Okay. And next, about the types of joint, we have a prismatic joint. So degrees of freedom for this prismatic joint is 1. Okay, for example, you have a screw and nut, rack and pinion. These are prismatic joints. Okay, has degrees of freedom 1. And next, this is revolute joint, only one rotation, and for this also you have degrees of freedom as 1. So we have a twist joint, you could see here. So here one link can move with respect to other in 3 dimensions. So that is your twist joint. Here also degrees of freedom is 1. And we have a spherical joint. So one link can move with respect to other in 3 dimensions. Okay. This same as a twist joint and spherical joint, but spherical joint has a degrees of freedom is 3. Okay. So twist joint degrees of freedom is 1. And next, cylindrical joint. Here we know that we have two rotations. Okay, so you have one prismatic and one rotation, so it has degrees of freedom is 2. And next is planar joint. Okay, so here you have one rotation, one revolute joint and 2 prismatic joint. Okay, so degrees of freedom for this planar joint is 3. And we have the universal joint or hook joint. For this, degrees of freedom is 2. Okay, so what is this universal joint? Is a positive mechanical connection between rotating shafts, which are usually not parallel, but it is intersecting one. So this is used to transmit motion, power, or both. So it is a rotary joint with 2 degrees of freedom. So this is about the joints and its description. So it's an overview of the types of joint. Okay, so we can see here linear joint. So here it is a type L joint. The relative movement between the input link and output link is a translation sliding motion. We know that for linear joint with the axis of two links parallel. Okay, next orthogonal joint here. So this is type O joint. We say it as relative movement between the input link and output link is a translation sliding motion. Output link will be perpendicular to the input link. You could see in the picture. Okay, next is rotational joint. So R joint. This provides a rotational relative motion with the axis of rotation perpendicular to the axis of input and the output links. Okay, and next is a twisting joint. The T joint we have seen. So this provides a rotatory motion, but the axis of rotation is parallel to the axis of these two links. And last is the revolving joint. This is type V joint. So axis of the input link to the axis of the joint, and the axis of output link is perpendicular to the axis of rotation. Okay, so these are the different types of joints. Okay, so degrees of freedom of a joint. So here first you can see in the first picture. So this indicates the number of rigid bodies, links that can be connected to a fixed rigid body through the said joint. So here this joints with 1 degrees of freedom. That is a revolute joint we have seen earlier. And next picture you could see here joints with 2 degree of freedom, cylindrical joint. And third you could see here joints with 1 degrees of freedom, that is a prismatic joint. And joints with 2 degrees of freedom, that is universal joint. So whatever we have seen earlier, that represented as a manipulator. Okay, and these are all the manipulators, that is the joints with 3 degrees of freedom. Okay, so ball and socket joint or spherical joint, all this we'll see a video. Please hold on.
Please.
Most common type of joint is the revolute joint. It places 5 constraints on the motion of a second spatial rigid
So
body.
for your
relative to the
better
first,
understanding,
and
you could
therefore
see
the
this
second body has
video
only
of
1
different
degree
types of
freedom relative
joints.
to the first body, given by the angle
This is
of the
revolute joint.
Another common joint with 1 degree of freedom is the prismatic
prismatic
joint, also
joint.
called a linear joint. We can also have joints with more than 1
Universal
degree of freedom,
joint
like
or
this
hoop
universal
joint,
joint, which
what
has
we
2
have
degrees
seen.
of freedom. The spherical joint, also called a ball and
This is
socket
spherical
joint,
joint,
has
3
3
degrees of freedom.
The 2 degrees of freedom of the universal joint plus spinning about the axis. This table summarizes the previous 4 joints plus 2 other types of joints. The 1
So
degree
these are
of
the
freedom
types
helical
of
joint
joints,
and the 2
whatever we
degree
have
of freedom
seen.
cylindrical joint.
So whatever I have shown you on the video, so the types of joints are planar, cylindrical, spherical, twist joints. Okay, so whatever I have shown in the video and whatever is explained earlier. We'll see now one numerical example. Okay, so this is about the planar manipulator example. First 2 examples. So first we'll see serial planar manipulator and second is parallel planar manipulator. So we have to remember, by using Gruebler's criteria we will be calculating the degrees of freedom. So for this planar manipulators we are going to calculate the mobility or degrees of freedom. Okay, so we have seen that Gruebler's criteria for planar manipulator will be maximum will be 3. Okay, so the formula varies only in that. Okay, so we have 3n minus summation of I equal to 1 to m 3 minus ci. So we know what is n and what is ci, the connectivity, all those things. So first coming to the first example, serial planar manipulator. Here, so what is n? Here n is the number of links. Okay, you can see here you have 1, 2. Here we have a prismatic joint, so you have 2, 1, 2, 3, 4. Okay, so you have here 4 links and m is the number of joints. Okay, so you could see here you have base 1, 2, 3 and 4. Okay, So constraints here, the connectivity, that is connectivity is for this planar manipulator is taken as 1. Okay, so from this we will be able to calculate by using Gruebler's criteria the degrees of freedom. Okay, so for this serial planar manipulator, for this degrees of freedom is 4. Just substitute in that formula, you will get the mobility. Okay, next coming to the parallel planar manipulator. Okay, how here the number of joints are calculated. So here we have seen that if it consists of a fixed base, a revolute joint, 3 legs and a top plate you have. Okay, so which is nothing, top plate is nothing but the end effector, you could see here. So at each leg we have got 2 revolute joints and a prismatic joint. So now we have to count how many constraint is there and how many joints are there. Okay, so that we have to count now. So we have got the 2 links. So for the 3 legs we have got 6 links. Okay, got it. And the end effector will be considered as 1 link. So we have got a total of 6 links. Okay, so you understood this. So that is we have got 2 links. So for the 3 legs we have got totally 6 links. And end effector is 1 link. So totally 6 links plus the end effector. So that is why here it is n is taken as 7 links. Okay. So we have got n, that is the total number of links is 7. So on each leg we have 3 joints, you could see here. Okay, that is multiplied by the number of legs. So we have got 9 joints. Got it? How we have got the joints. So these joints are on each leg. We have 2 revolute joints and 1 prismatic joint. Okay. So now how will you calculate the connectivity is given here. CA is 1. But how this connectivity has obtained? Okay. So each of these joints has connectivity of 1. Which means each joint is going to put, that is we know that the summation, that is 3 minus Ci, you could see here the connectivity. So the constraints for each joint is here, it is taken as 2. Okay, so 2 constraints for each joint multiplied by 3 joints. So hence each leg is going to give 6 constraints. So for the legs we have got 18 constraints totally. So total number of constraints, which is a summation on I from 1 to m, that is the number of joints for each leg, is going to be nothing but, that is a summation I equal to 1 to m 3 minus Ci. So for that is totally you will get 6. For each leg you will get 6. So for the 3 legs you will get as 18. Okay. So from this we will be able to calculate the mobility of the parallel plate manipulator. So here it is 3. Okay, so degrees of freedom is 3 degrees of freedom for the parallel plate planar manipulator. Next, parallel spatial manipulator. So spatial manipulator is only there is a slight variation in the Gruebler's criteria formula, as you will be taking it as 6n and 6 minus Ca. Here you could see here n is the number of links and m is the number of joints. As we have seen in the parallel planar manipulator, the similar explanation we can remember it for the parallel spatial manipulator. Okay, here you could see we have number of links. Okay, on the base we have 6 links and the links connected to the top plate, that is end effector, is 6 plus 1 end effector. Okay, so 6 plus 6, 12 plus 1, that is 13. So totally we have 13 links and m is the number of joints. Okay, so here we have 6. So and at the end effector we have 6. Okay, and here we have a different prismatic joints, 6 prismatic joints. So 6 3s are 18. So we have 18 joints. Okay, so from which we are able to calculate the degrees of freedom of the parallel spatial manipulator. Okay, So this is about the degrees of freedom, links, joints, and we have seen various types of joints and how to calculate the degrees of freedom by using Gruebler's criteria for both planar manipulator and spatial manipulator. Okay, thank you.